Heating effect of electric current. Let's understand the heating effect of electric current in this video. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. In order to maintain the current, the source has to keep expending its energy. However, a part of the source energy in maintaining the current may be consumed into useful work, like in rotating the blades of an electric fan. Rest of the source energy may be expended in heat to rise the temperature of the gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time, etc. On the other hand, if the electric circuit is purely resistive, that's a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is Vq. Therefore, the source must supply energy equal to Vq in time T. Hence, the power input to the circuit by the source is P is equal to V into Q by T, or P is equal to V into I. Or the energy supplied to the circuit by the source in time T is P into T, that is VIT. This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time T is H is equal to VIT. Applying Ohm's law, that's V is equal to I into R, we get H is equal to I square RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of the current for a given resistance, directly proportional to the resistance for a given current, and directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a non-voltage source, the equation representing Joule's law can be used. After calculating the current through it using the relation I is equal to V by R.